everybody. Thank you very much indeed for coming to Cosmic Frequencies 2025 here in Exton. That was the music of SKX Funkanauts. We will have more of them later in the show. My name is Bill Garrett. I'm your Master of Ceremonies, pusher of buttons, general producer of the show with my two fine colleagues Mike Evans and Nick Skelty. So it's kind of being run on a budget, so we hope we're doing quite well. Again, thank you very much indeed in trusting us and coming to the show. We have a stellar cast of people to talk about this subject area of the existential question, are we alone in the universe, and have they come and visited us? So, we hope you will be enlightened. There are no solid answers to these questions. All we can do is provide you with some information and a very wide-ranging perspectives on this subject area.
There we go. So I think this is a really good place to start, actually, by looking at the scale of the universe and just looking at the sheer size of everything that we're contained within. And I can make this talk really, really short, actually, just by saying something such as space is just big. And that will be it. More, I'll give you more. Give me 1 second. Space is this. And that's it. No, I'm joking. I think a really good place to start whenever we're talking about the scale of the universe is probably just by looking at our local environment to the universe. And a good place to start with that is with our sun. Our sun, this image was taken by, well, it wasn't taken, it was drawn by Galileo back in the 1600s. And I love it because you can see some features, and this was really the first time that anybody had confidently suggested to the entire world that the sun was a physical entity, spherical, with features. He was really pioneering the idea that the sun was a central piece of our universe at the time. We were on this vessel going around this object. The first time that it was starting to be accepted by the masses, and arguably you could say this is when astronomy first became a subject. Prior to this, everything was a little bit more philosophical, a little bit more spiritual in some cases, and we can go down the route of talking about astrology, but we're not going to do that right now. Instead, I want to talk about just the sheer size of our sun to begin with. It's absolutely ginormous. About 109 times the width of our planet, just under 1 million miles wide. And you could fit inside of our sun, inside of its volume, about 1.3 million of our little planet Earth. And you can see, just against the rest of the planets in the solar system, just how big this object is. In fact, if you got all of those planets there, and all of the other stuff that you could see in the solar system, all of the mass of our solar system, and you made it into a big pile, the sun would still be 99.86% of your pile of stuff. The sun is overwhelmingly the most massive object in our solar system. And it all started life inside of a ginormous gas cloud. It's very different to the planets. The planets are going around our sun, and the big distinguishing difference is that this thing came first as a result of a big stellar nursery, such as what we're seeing here. This here is the Eagle Nebula, arguably one of the most famous nebulas taken in the mid-90s by the Hubble Space Telescope, these beautiful pillars of creation, as they often get called as well. And inside of a big cloud, or a cloud complex such as this, is where stars start to form. And the reason why stars start to form is often because of gravity. So really, just talk about gravity for a second, because I think gravity, we often get taught about gravity as if it was a kind of mythical, magical thing that happens, that keeps us on the ground. Apples fall out of trees because of gravity. But actually what gravity is it's more of a distortion of space when you put something in it. So if you imagine the vacuum of space with nothing in it, a line would just go straight through it. Until you come along and you put some mass in that universe, and then what would happen? is that line would start to bend around that object. It distorts. Space does introducing mass into it. So now if you imagine, if you're a little hydrogen atom, your little hydrogen atom has mass, and your area around it is being distorted. So if something comes too close to that, it's going to fall into it. Just like we're currently falling into our planet, because our planet is distorting space, so we're falling into our planet right now. Now if you've got another hydrogen atom that should come along, well, the two of them, if they get too close, those little wells that have now been created overlap, and they'll fall towards each other. Well, they don't want to stick to each other. The hydrogen atoms, they hate each other. They're a little bit like, it's like trying to get pandas to mate. It's not going to happen. They hate each other. You've got to really force them together. And so what happens here is, you get maybe two hydrogen atoms that are really close, and then another one drifts by at the right moment that it gets dragged in, and then another one gets dragged in, and then more and more and more. The more and more hydrogen atoms are getting amassed in this little area, the more and more the well is starting to increase, more and more starting to get pulled into this mess, until it reaches a point whereby there's so much stuff now trying to stick together, fall into each other, that the pressure right in the very centre is incredible enough to be able to force these hydrogen atoms together. And this is hydrogen fusion. And this is what brings suns like our sun to life. And continues to fuel our sun, is hydrogen fusion, at a phenomenal rate, in fact. So this process happens in phenomenal quantities every second. About 400 million tonnes of hydrogen is turned to about 396 million tonnes of helium every single second in our sun, which is a strange number because we're putting in some hydrogen and getting out helium, but we're getting less helium out when we do that. And as a result of that, 4 million tonnes of mass has disappeared in that little equation we did there. So where's that gone? Well, that becomes energy. And it's the energy that we can see, the light that we can see. And our sun will go on to create more elements in the periodic table, and that's kind of the job of a sun, is to produce elements in the periodic table. But not to dwell too much on the physics of all of this right now. I want to go back to talking about scale. We'll just give you an example of what's going on in our locality and what these things are that we're going to be talking about here. So that's our sun. Okay, there's a big picture of it. And you get to see these incredible features. I love this video, these incredible bands of light coming out of our sun. It's an incredible beating heart of our solar system. But the problem is with space is that everything is just so unbelievably far away. Our sun's 93 million miles away from us. The moon is 250,000 miles away from us. And even when you put it on the screen here, look to scale, that's a really long way. And we sent people there back in the 60s and the 70s, all that way to the moon. People always say to us, Dan, why have we not gone back to the moon since the 70s? It's because it's really far. How much is fuel? It's really expensive to get these things to the moon, and there's so much going on this rock. But then when we start to expand away from our sun into the rest of the universe, the numbers become really, really uncomfortable. And so I've armed each of you, or hopefully armed many of you, with a bouncy ball. And this is when your bouncy ball comes in useful. Please don't throw it at me. You can later if you want to. Well, your bouncy ball is 24 millimeters in diameter. This is your little personal sun. And I want you just to keep a hold of your little personal sun for a second. All of these stars that we see on the screen right now, this incredible structure here that we see in the middle of the Milky Way galaxy that we live inside of, all of those stars, they're suns, just like our sun, just really, really far away. And we did actually get taught this in the 90s, actually, by Father Ted. Things in the distance, they just seem smaller, right? They're just really, 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 really far away. So how far away are these objects? Well, your little sun's 24 millimeters. On that scale, if we shrank the sun down to the size of your little 24 millimeter sun that you've got there, on that scale, the Earth would be about 2.6 meters away from the sun on that scale. Whereas if we moved a little bit further away from the Earth and went to somewhere such as Pluto, Well, for Pluto, we'd have to go a little bit further than this room. In fact, we'd have to go all the way over to Tesco, about 106 metres away on that scale. Well, what about the nearest star? The nearest star is 4.24 light years away. Light years, 1 light year is a unit of measurement of 6 trillion miles. 4.24 of those on that scale would push you way beyond the boundaries of the UK, across to somewhere in the region of Luxembourg. That's where our nearest star would be on that scale, with the Sun just being 24 millimetres wide. Well, what about even further away than that? Well, I had to change the animation actually when I got to this scale. I had to switch to a different piece of software. If we were to move outside of our galaxy and go to somewhere such as the Andromeda Galaxy, our nearest neighbouring galaxy, that would be way beyond the confines of Earth, way, way out there, somewhere in the asteroid belt on that scale. And the galaxy itself would be about 1,200 times the size of the Sun. So imagine your little Sun there, times it by 1,200, that would give you an approximate size of things. Okay, so things are really, really big out there. And around each of these suns is planets. Something that was theorised back in the 1500s, in fact, by this chap here. His name is Giordano Bruno. He was quite a trailblazer at the time and believed in some incredible things. Bear in mind, this was before we got comfortable with the sun being the centre of the universe at the time. This chap was saying all of the stars in the night sky, they're suns with planets going around them, just like Earth goes around the sun. You can imagine how popular he was in the 1500s for this. He travelled across Europe, kicked out of practically every country that he visited, until he eventually went back to Italy. God knows why, but he was coaxed back somehow. And then in the year 1600, he was dragged out into Campo de Fiori in Rome, tied upside down to a pole and set fire to, just because he thought that there was other planets going around other suns. Can you imagine that kind of persecution? Anyway, turns out he was right, wasn't he? We didn't find that out until 1992 though, and now we found about 6,000 of these things orbiting around other star systems. So now the kind of structure of the universe, if you like, is you've got suns with planets going around them. Is there bigger structures? Yes, there is, and it was a local astronomer who really started to pioneer this, and you've kind of had a glimpse of this bit already, but this here is Thomas Wright. He was from Bishop Auckland in County Durham, and Thomas Wright said, when I look up in the night sky, can you imagine what the night sky would have been like back in the 1700s, which is when he suggested this? It would have been amazing. Everybody would have had a dark sky in their back garden. And he said, I think this band of light that I can see in the sky, I think this is actually an island of stars that we live inside of, one filled with billions and billions of stars. And he termed it an island universe, which went on to influence the works of Immanuel Kant. And then he suggested that I think there's other island universes out there as well. And it turns out he was absolutely right. If you look around our planet, you can see the structure that surrounds us, this band of light. We're inside of the Milky Way galaxy, or as he termed it, his island universe. This flat disc-like plane of stars filled with about 400 billion stars, and our sun is just one of those. And this entire structure is about 100,000 light years in diameter. So again, 100,000 times 6 trillion, that's your distance in miles there. This thing is absolutely ginormous. So what about that other place as well, other island universes? Well, they do exist, but we didn't get to know that they existed until about 100 years ago, when somebody, a quite famous chap by the name of Edwin Hubble, he's got a telescope named after him if you're not familiar, found that this thing is outside of our own little island universe, the Andromeda Galaxy, and it took an image of the Andromeda Galaxy, which I think is amazing. And when we start to zoom into this image, it was such a high resolution image, you can see all of these little tiny dots that are on the screen right now. Each one of those is a star inside of this galaxy over here, a galaxy filled with about maybe 500 billion stars in it. This thing is absolutely ginormous, and that's just one of, well, many galaxies out there. And it's in this image right here. The lighting in this room doesn't do it any justice, but it really jumps off the screen when you put a circle around it like that. So there it is. Quite hard to spot. You can't see it with the naked eye. It's an incredible structure, but just one of trillions and trillions and trillions of galaxies which occupy our universe. Almost a countless number. We don't know where it ends. We have only the evidence as far back as we can physically see, and beyond that, well, we can't see anything. But one thing that we can see is that structure starts to develop an incredible web-like shape where things are clustered together on what starts to look a little bit like the neural pathways of a brain, and I think that's really quite intriguing. And that's it. Thanks, guys.
We have one very quick question for you now. Your context of your presentation is very much about the enormity of the universe and our very small place in it. We have started to, as a scientific exploration pitch, understood that there are exoplanets. I think the closest is about 4.6 million light years away. Is that correct? What, in your view, as a professional astronomer, are we in a position to understand that we are alone or we are unique?
It's a really hard question because, everybody argues with each other. The beauty of science is, to the professional scientific realm, and using the word professional astronomer is a very inaccurate word to use for me. I'm certainly not that. But the scientific realm is well known for its arguments, its debates, and its very contrasting views. There are people who think that there is a likelihood that there could be life somewhere else, which is very similar to us because the numbers statistically make it feasible. And I think that's the only way that you can really comfortably start to work through that, is to look at the numbers and look at the statistic possibility of it. But certainly the way that I find it more comfortable, and I'll give you one statistic on that, which is that when you look at the rest of the universe around us, there's about 100 sextillion stars that we can see. And that number is so big, it's got 22 zeros on the end of it. And the number, to give you some context on that, is about 10 times the amount of grains of sand that we think occupy our little planet here, there or thereabouts. It's very rough maths. And so 10 times the amount of grains of sand on our planet, that's how many stars there are. And then you could say, well, okay, out of all those stars, which ones could be habitable? Which ones are like our sun, and you can start to dwindle down those numbers, and then you can say which is in the habitable zone, which actually I don't think is a place that we're going to find life in our solar system, to be honest, next, and I think they will be found. So even the numbers start to lose sense at some point as well.
Do you think the Drake equation, sorry to remind anybody who is not familiar with the Drake equation, this was an equation created in the 1970s by a group of very prominent scientists and astronomers and astrophysicists who sat down and tried to calculate what is the possibility of life within our galaxy. Now that was a very blunt equation. They came up with some really quite deep assumptions. Do you think in the last 50 years, the profession of astrophysicists and scientists and astronomers would now look at that equation and say, okay, we need to rethink it. It's probably, now we see that the uniqueness that has created life on this planet is probably much more complex, and therefore the Drake equation may now need to be rethought. Do you think that's a point?
Yeah, definitely. I think when you've got something that's 50 years old in science, it is absolutely well out of date. I mean, we haven't even discovered exoplanets at that point, arguably. So there's, that should be looked at again. And it probably is looked at again, in fact. I can't think of whether or not it has off the top of my head, but yeah, it should be. Yeah.
Okay. Thank you very much, Dan.
Cool.
Okay.